Hey friends, it's Miss Adams from Flamingo Math. Let's continue looking at matrices as functions in this first lesson of 413. We have 3 different lessons in this section. So basically in this lesson, we're looking to determine the association between a linear transformation and a matrix. First of all, let's think about the linear transformation in 2 dimensions. If we have the first term in X and the first term in Y, row 1, column 1, row 1, column 2, we're adding those together. Row 2, column 1, row 2, column 2, we're adding those together. That's going to be associated with this matrix. Let's explore how that's related. If you consider matrix A, we want to show that matrix multiplication of A transforms a 3-dimensional vector into a vector in 2-dimensional space. We need a 3x1 matrix to produce that 2x1 result. If you remember from earlier about matrices, if we have this 2-row, 3-column, this 2-row, 3-column matrix, and we're going to multiply that by 3 rows, 1 column in matrix B. The column and the row have to be the same in order to multiply, and when we finish the multiplication, we'll have a 2-row, 1 column, 2-row, 1 column matrix after the matrix operations are done. So let's give that an exploration here in part A. So here we have matrix A times matrix B. Performing that matrix multiplication, we have 1 times 1, 2 times 2, and 0 times 3. And then we have 3 times 1, 1 times 2, and 0 times 3. The result is going to be a 5, 5. So we have 2 rows, 3 columns. By 3 rows, 1 column, we end up with 2 rows, 1 column, which is what was stated initially. We want to use the column matrix XYZ to give a generic example. And setting that up, it's going to be X plus 2Y and then 3X plus Y for that general example. The example above demonstrates the transformation that we achieved by matrix multiplication. And we've already seen the notation. The transformation of vector X means the transformation applied to the vector X. We can write that transformation A of X as A times vector X. Our notes here are simply restating some of the things we've seen in previous lessons with the scalar multiples and the dimensions being in real numbers to the dimension n power. We've already talked about this linear transformation definition in our last lesson, so I'm not going to go over those again. We want to introduce what's called elementary vectors here. The vectors along the standard rectangular coordinates in 2-dimensional space are noted with E sub 1 is 1, 0, and E sub 2 is 0, 1. So this is in the X direction, and this E sub 2 would be in the Y direction. That's why we're calling them the ordered list. E sub 1, E sub 2 is going to be called the standard basis of 2 dimensions. Let's look at example 2 to get an idea of what's happening here. We want to find the standard matrix for the dilation transformation of 4 times vector X for X in 2-dimensional space. So we can use these elementary vectors and do the transformation of E sub 1 as 4 times E sub 1. So 4 is our scalar, and E sub 1 is 1, 0. That gives us 4, 0. So we dilated E sub 1 with that transformation, and our scalar is a factor of 4, and then doing the same thing with e sub 2, 4 times 0, 1 gives the transformation 0, 4. So putting that together, we can call vector A, the transformation of A, is going to be 4, 0, 0, 4. So we found the standard matrix A for the dilation of t on x, where the scalar was 4. Then we want to find the determinant of A. So the determinant of A is 4 times 4 minus 0 times 0. So 16 minus 0. Our determinant is 16. And I need to fix my notation here. It's not a bracket. It's a straight absolute value bar for determinant. And then tell what that value does to the dilation in 2 dimensions under that transformation. So the absolute value of the determinant is going to give the magnitude of the dilation of regions in 2 dimensions under the transformation. Let's write that in a nice, neat sentence here. So we can state that again here in that complete sentence. What the absolute value of the determinant does is tells us the magnitude or the length of the dilation for regions in R2 under the transformation. I'm thinking back about that little sunshine with the sunglasses from several lessons ago. Let's look at example 3. We see that the identity matrix has been divided up into 2 elementary matrices that we're calling E sub 1 and E sub 2. Suppose that the transformation T is a linear transformation that's going from 2 dimensions to 3 dimensions, and we know the transformation is given by this first column vector and then this second column vector. We want to use these two to write a formula for the image of an arbitrary x in 2-dimensional space. But first we're going to explore how we got to these 2 transformations. We can set that up using the rule that we saw in the notes previously. We know that the transformation vector on some arbitrary x comes when we do the x sub 1 vector times the transformation of an elementary vector plus x sub 2 vector times the transformation of elementary 2. Using the example they gave us, we have x sub 1 times the transformation, which was given as 2, negative 3, 1, and then x sub 2 vector times the second transformation, negative 4, 6, negative 1. Multiplying that out, we have 2x sub 1 minus 4x sub 2, negative 3x sub 1 plus 6x sub 2, and finally x sub 1 minus x sub 2. So this is how that transformation of x came. And writing that arbitrary x, the transformation of x bar would be the transformation of e sub 1, transformation e sub 2. So that matrix times the 2-dimensional x1, x2 produces that A matrix times vector x bar. This is the final result of how we can rewrite the transformations as a matrix operation. In our next example, we're going to look at using technology. I've given the instructions for the TI Inspire CX calculator. And what I did here was use this menu, these keystrokes, to set up a matrix. We're going to set up a 2-row by 4-column matrix. And I want to just write that down here. You can see in the bottom in step 3 how I'm writing that down. I want to do reduced row echelon form so that we end up with the identity matrix on the left and our solution matrix on the right. So we're going to write into our calculator 2, 1, negative 2, 5. So we want 2 rows, 4 columns, and then second row 1, 1, 1, 3. Now if we were working this out by hand, I'd put a little dotted line there. Next, we want to use the solve using the reduced row echelon form for x1 and x2. And you can see our calculator is going to give us that solution set here. Remember, the identity matrix is on the left and our solution matrix is on the right. So we want to use that. 1, 0, negative 3, 2, 0, 1, 4, 1. This is our solution that we got from the calculator. This is our identity matrix here. And we're going to put that together to determine whether our solution X is unique or not. So the general idea is that we have to have some A times X bar to give us those B values. And that means, if you think about it, we need to have our X equation, our X matrix, to be an X sub 1 term, an X sub 2 term, and an X sub 3 term. So this is what we're looking for. But we have a 2-row, 3-column matrix. So we had to determine what the value for x3 is. If you think about this solution set that we got from our calculator, if this is x1, x2, x3, that has to be our B value. So what I'm going to think about is x1 minus 3x3 has to equal 2. So our x1 term in our matrix would be 2 plus 3x sub 3. And then looking at the second column, this is x1, this is x2, this is x3, and that's our B. So x2 plus 4x3 has to equal 1, which means our x sub 2 is going to be 1 minus 4x sub 3. So we have that equation. And then what would be our x sub 3 equation is free and open, because we don't really know whether this number is fixed and our x bar is unique or not. So let's just try some examples. For example, if we let x sub 3 be 0, then we're going to end up going back here to substitute 0 here and 0 here. Then our x bar is just going to contain 2, 1, 0, because we have a free space in x sub 3. But what would happen if we let x sub 3 be 1? Then if x sub 3 is 1, we end up with an x bar that is 2 plus 3, 1 minus 4, and 1 for our x sub 3. If these two x bars are different, then we know that our x bar is not unique, and we have satisfied that example. And what that tells us is that there is no unique x bar, and this particular transformation would have an infinite number of solutions. You could substitute any value for x sub 3. For this last example, we want to look at how we can use a matrix to cause a clockwise or a counterclockwise rotation using some trig properties. The matrix that's associated with linear transformation of vectors that maps every vector to the vector that is an angle theta in a counterclockwise rotation about the origin from the original vector is this vector A, where the elements are trig functions, cosine, the opposite of sine, sine, and cosine. Let's see how that works, because we'll explore this more in the other two lessons that remain. Say we're given the vector 3, 4, and we want to rotate that vector counterclockwise pi over 2. So I want to just draw a picture real quick, sketch that for us, so we can see how this happens. We've got our x and y axis here. And our vector is located at 3, 4. So it's 3 units out, 4 units up. And that's our vector there. We're going to call that vector u. And we want to rotate in a counterclockwise manner pi over 2. So that's our angle of interest right here. And we can use vector A, so we want the cosine of pi over 2 and the sine of pi over 2, the opposite of the sine of pi over 2, and the cosine of pi over 2. This is our rotation matrix, and we're rotating vector 3, 4. So that's a column matrix there. Cosine of pi over 2 is 0. The opposite of sine is -1. The sine of pi over 2 is 1, and cosine is 0. Doesn't that look familiar from our earlier lesson with the sunshine and the sunglasses? And the parallelogram, we rotated all of those. Moving through the multiplication here, 0 times 3 and -1 times 4 gives us 0, slipping here, 0 minus 4, and then 1 times 3 and 0 times 4 is going to give us the rotation -4, 3. And we can sketch that on our graph, go -4 to the right and 3 units up. This is vector V, -4, 3. And we know that the magnitude of vector u is 5. The magnitude of vector v is 5. They're equal to each other. And the determinant of vector A is going to be, 0 minus -1. So the determinant of A is 0 minus -1. The determinant is 1. You might recall from geometry that we could also kind of mentally do this in our head by if we swapped the x and y coordinates and then made the y value negative, that would switch the vector 3, 4, interchanging y with x would be 4, 3, and making the y coordinate negative. -4, 3 is that mental check from geometry that verified this rotation matrix on our vector 3, 4 actually rotates 90 degrees in a counterclockwise manner. We'll see more of these in the next lesson. Join me there.